Hello and welcome. In this video, I'm going to talk about Liskov substitution principle. It is also short form for LSP, or it is also full form for LSP or LSK, or because Liskov is the guy. Okay, so let's see what the principle tells us. It's a complex, but let's try to understand it via example. Okay, so let Q of X be a property provable about objects of X, okay, of type T. So we are saying that Q of X is a property which is provable about object of X of type T. Then Q of Y should be provable for objects of Y of type S. Why is that? Because S is a subtype of T. So wherever S is a subtype of T and we are saying Q is a property which is provable for objects of type T, then Q should be provable for objects of Y which is of type S, where S is a subtype of T. Okay, now let's try to understand this via example. Okay, take a look. I have this interface car over here which has these two contracts, or which has these two properties which are provable. So when I say car, I can say that a car have an engine, and I should be able to turn the engine on, and if it is a car, then I should be able to accelerate the car. Okay, so this is the contract of the car which says any car I can turn on the engine or I can accelerate it. Okay, now take a look at this nano car. Okay, so Tata Nano, which extend this car. So here we have a car type. Okay, and for any object of car, we should say that properties turn on engine and accelerate are provable, means we can call them in simple words. The Tata Nano, which is a subtype of car. Okay, so any object of Tata Nano should be the properties, the turn on engine, which is Q. You can refer these two as Q over here that we mentioned earlier. So Q of X is nothing but object called like, let's say, car object called for this property Q, or this property accelerate. Okay, same case for the Tata Nano. Accelerate and turn on engine should be provable because it is a subtype of car. So since car, in the case of car, these two properties are provable, so all the subtypes of the car, the object of these subtypes must have these properties as provable. Okay, so in case of Tata Nano, we can have these methods like this, and I'm just printing something related to that. So accelerating nano and turning the nano engine on. So we're not breaking anything over here. This is a valid, good example. Now let's take a look at another thing, which is a Tesla Roadster. So the Tesla Roadster is also a car, and it is extending this car interface, and since it is implementing actually this car interface, then it has to implement both the methods, which is turn on engine and accelerate, to follow the contract. Okay, now in case of accelerate, Tesla Roadster says okay, accelerating Tesla, but in case of turn on engine, Tesla doesn't have any engine, so it works on motor with batteries, so it doesn't know what to do, so it throws an exception, and this breaks the Liskov substitution principle, because the property Q, which is turn on engine, is not provable for the object of type Tesla Roadster, okay, which is a subtype of car. So that's how it is. So yeah, that's all. And in order to refactor this, it's really hard because we have this contract, and we can use, I mean, it's not like we cannot do that. We can move this method to another interface where we say engine car, and then the normal car interface will have only one method, which is accelerate, and then but the problem that there is that we'll be breaking open close principle, because there might be some third-party libraries which are using this car interface, and then they have to, wherever they have implemented this interface, they have to change the contract of it. Okay, so that's how it really is. So yeah, that's about it, and in the next lecture we'll be seeing this interface segregation principle in action. So let's see.